Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right, hello everybody.
Yeah, that was close.
Oh, that was close.
That was close. As in, I clicked the button. I'm not paying attention. I'm just talking to you about other stuff. And you're like, hey, there's 6 seconds left.
Yeah, 6 seconds left.
I was like, not paying attention at all. Welcome everybody. Hello, I'm a professional.
Yes, welcome to another episode of Ask Us Anything about electrochemistry.
Good grief.
And we're happy to be back. I don't know if you recognize, we weren't actually here last week.
We were off last week. Yeah, it was really nice to have someone fill in for us.
Yeah, we managed to get Professor and Socrates to attend this this live stream, answering a lot of the questions.
They did a pretty good job for a couple of dead guys.
I know. Pretty good. Good.
I was impressed. I think they were very good-looking gentlemen as well, if I do say so.
Yeah, not bad.
Yeah.
Not too shabby.
Very good.
Not too shabby.
But we're back triumphantly. And the creepy text is gone.
Yeah, because it's no longer Halloween.
It's not Halloween anymore, and it was not possible to read that text. I was definitely okay with it because it was kind of funny, but it was not possible to read it. So there you go.
Yeah.
And then the other thing that I will say right off the top, we'll probably mention it periodically as well, is right here on Wednesday, next Wednesday, join me, register. pineresearch.com. I probably have that on the thing. We don't, but pineresearch.com/webinars.
Or go to our website and click on webinars. That's the other way to get
that
too.
Yeah. If you really want to find it, you'll find it. It's not that hard to find. Yeah. But I'm doing a webinar next Wednesday, 2 time slots, 8 a.m. Eastern time, which is 13 UTC, and then 16 Eastern, which is 4 p.m. Eastern, which is 21 UTC, which is what that's 9 p.m. UTC, I think.
UTC is what part of the world?
UTC is like it's universal time clock. What the heck does UTC stand for? It's like it's England somewhere in Europe, but it's universal coordinated time. What is it? Yeah, coordinated universal time.
But why isn't it CUT?
Probably because it's like French, maybe.
Oh, okay.
Maybe not. It's universal time coordinated. I don't know. You're asking a lot of questions of which I don't know. All I know is
that you get off your back about that.
Yeah, you should get all the way off
your back about that.
All I know is that that is something that at least Europeans, I believe, are somewhat familiar with for like referencing. Because if you're in like Spain or Germany or somewhere, it's like UTC plus 1 or.
Oh,
right.
Okay. They just have to add it by like 1 or 2.
1. Exactly.
Yeah.
So that's referenced to, I think, the UK. But anyway, the point is, not everybody works based on America time. Some people work based on the UTC time. If you're in India or China or Japan, it's like, UTC minus 5 to 6 or whatever the number is. Anyway. The time slots are there on our website. Join me. It's a webinar on Mott Schottky. If you want to know more about Mott Schottky, you want to see me do Mott Schottky, all the Mott and all the Schottky that you can handle next Wednesday. Join me. And we will get right to it now after all of that preamble here. There was a question from Joe Duerden. Duerden. Joe, not that long ago with a good set of questions here. So it says, hi guys, I'd like your take on a debate within my research group. Oh boy. Now we're going to take the debate stage.
Yeah.
When conditioning an electrode, which is a 500 micron polycrystalline platinum in dilute, this is really dilute, 20 millimolar sulfuric acid by CV at 200 millivolts per second, we see the CV, quote, improve with oxide formation and hydride peaks forming and leveling out. Full disclosure, I don't really know what the hydride peaks are.
It's the butterfly part. It's those
platinum hydride. Oh, okay,
yeah,
okay.
it's
Is that what
different.
you're referring to? Okay.
Yeah, different crystal faces of the.
I was thinking
platinum.
you mentioned it
Yeah.
in reference to the oxide formation, so I was thinking it was something on the positive end. But yeah, if you mean the platinum platinum PTH butterfly, but then
PTH.
that's in the negative region. Okay.
Yes.
Yeah,
I think so. I think that's what
that's that.
they're
I think you're right. Yeah, yeah. Okay, so it levels out. Improvement is maybe not exactly the right word. I mean, it's maybe it's changing, but in any case, the question continues. Using a high-speed EIS technique we developed, which I don't know what that means, but okay. We see surface capacitance calculated by CPE increasing and leveling out during the CV. Okay. So the question is this simply roughening of the electrode surface, or is it a mix of roughening and cleaning, removal of impurities from the electrode surface? Thanks. So my first thought, or I don't know, answer to you is that one way that you could, in theory, answer this question would be to look at the alpha or n, whatever the variable your software uses, basically the exponent of the CPE, whatever that is, can inform you the answer to this question. As a general rule of thumb, if you will, maybe it's not always the case, but it is, I would just say, often considered the case that one of the reasons why a CPE, for instance, is used is to account for non-idealities in a capacitive effect. And one of the ways that non-ideal behavior occurs is through heterogeneities in the surface or rough surfaces. So for instance, you could theorize that, for instance, as you perform your CV, if the alpha value initially is closer to 1 and it decreases over time, that would be evidence, or at the very least, let's just say, theoretical evidence. Like it's not foolproof. Like precisely what the alpha means and why it's non-ideal. This is just one possibility. So I wanted to hedge a little and not say like this is definitely what it means. It's not exactly certain. So that being said, it is at least reasonable to suggest that if, for example, after a bunch of CVs, the alpha value has dropped from like 0.9 to 0.6, I'm just making up numbers, but let's just say it does something like that. One of the arguments you could make is an alpha of 0.6 indicates that the surface has gotten more rough. My capacitive effect or whatever, has become less ideal because the surface is now more heterogeneous or rougher or whatever. That would be one way, in theory, you could do that. Now, I guess the other part to say about this is that how rough can a surface really get from something as pretty benign as CVs and dilute sulfuric acid? I mean, I guess the surface will change. That's why we have to polish electrodes like after tests and everything like that. I would doubt that it would get like really rough per se, just from a handful of CVs. The kind of cleaning phenomenon, I guess, if you will, of doing multiple CVs on a platinum electrode is often, I find that also to be somewhat like nebulous in some sense. I mean, maybe there's better explanations in the literature, but it tends to fall under the category of the last part of your thought, which is like, oh, well, by sweeping over and over again, there will be a sort of settling of the curve into some repeated trace that it kind of traces over itself after a while. And that sort of is commonly thought of as what you said, like impurities are removed from the surface. You sort of reach a steady surface condition. So I think both are possible. And like I said, checking that exponent of the CPE could be a way to, in theory, provide evidence of such surface roughening. So I think it's definitely possible. But what I would say is that it's not like 100% guaranteed that that's the answer. I just wanted to clarify. So I don't know if you have anything to follow up on that. But
Yeah, I mean, I've always been, I guess, taught, if you will, that it's always a cleaning technique. But of course, there is. I can understand there being some surface roughening, and that would, in my opinion, only be due to, quote, the formation of the platinum oxide. You're forming a platinum oxide, you're removing the oxide. You do that multiple times, and so there is some roughening. So you see oxidation current in the platinum, and then you see its reduction. There's a huge platinum reduction peak, and then you see the hydride formation on the different like crystal faces. So I haven't personally studied or thought very much about the quote roughening, but the idea has been that when you're oxidizing the platinum surface, you're also oxidizing any potential organic stuff that could be on the surface, and that is the quote cleaning that is occurring. And so the potential window that you sweep between, because you can actually get it, like you could push it a little bit more oxidizing, you could push it a little bit more reducing, get a little bit of hydrogen to form. So I can definitely see a little bit of roughening of the surface occurring if you push the potential window. That's the only bit of information that hasn't been put into this in your question. It's like, oh, you sweep between the at 200 millivolts per second, but we don't know like exactly how much beyond from the platinum oxide reduction peaks are you actually sweeping from.
Yeah.
So that's the only other thing I'd think about. But
potential limits can definitely play a role in this kind of thing for sure.
Yeah, definitely. Like how fast, it's like, oh, if you really crank up on the oxide formation, then it'll end up cleaning faster and stuff like that. So hopefully that helps. I don't know if that's
yeah, give some of that some thought. Like you said, it looks like Joe responded. He'll have another look at that, another look at the alpha values. So hopefully that kind of oh, look at that, it's like backwards.
We can adjust that.
I don't know how to do that actually, because the caption ones were
here we go. So we have news.
It's weird that it puts it upside down.
That's
maybe it doesn't matter. I just noticed it. I don't mind that one. Maybe the black what's this one look like? Maybe that's better.
Yeah, I think
that's bizarre though.
It was just base.
Yeah, your question here. Yeah, it's like name on top, question below. Like that makes more sense to me.
Yes.
And then we did the live one. It was like, hey, let's put the name on the bottom. That's better.
Yeah,
I like that more.
And that font is okay.
Yeah, I don't mind the font so much. It's clear. It's not creepy.
Yeah.
So,
okay.
So anyway. this is very important stuff here. It's like
we just did the font one
time. We had to. I was playing with it earlier to get rid of the creepy, drippy Halloween one, and I didn't realize it was going to do that. It's backwards.
Yeah.
Order is not restored. It's It's upside down. I can't function this way. Well, now everything's back in the way of the world. And so Ali has a question: can we use a 2-electrode system in research work instead of a 3-electrode system in a way that is more accurate?
I don't know if you're going to get more accuracy in a 2-electrode than a 3-electrode system, but it depends on what you're doing.
It depends what kind of accuracy you're referring to
as
well. Like, what do you mean by accuracy? Like, just in terms of the measurement itself? Like, the accuracy of the measurement, broadly speaking, is dependent by the instrument. Like, the accuracy in the current or the voltage measurement or the potential measurement or whatever. All of that is like the same if you're using the same instrument. If you're talking about the accuracy of what potential you're at, no. Probably not. I mean, the reference electrode kind of necessarily gives you more knowledge of where your potential is. But if you're talking about accuracy in any other way, hard to know. Like I think it's a bit ambiguous. What you mean by accurate. But like things like batteries or supercapacitors or fuel cells sometimes are necessarily 2-electrode systems, and that's like normal, can be perfectly accurate. There's nothing sort of wrong with that, right? When you're talking about like a voltage or a potential difference, right, between just two anode cathode 2 electrodes. It's not inaccurate, sort of definitionally. I guess I would have a follow-up question, which is, are you, I don't know, having problems with the reference electrode to the extent that you're hoping you can ditch it and, you know, go with a 2-electrode system because the reference is causing you problems, and you're wondering if you ditch the reference electrode, will your measurements still be accurate? Like, will they still work or something? That to me sounds like the reason why someone would ask that question.
Ali is giving a little bit more
Okay.
kind of. He says, "I'm doing research on electrochemical oxidation, and I don't have access to 3-electrode system."
Okay.
It still doesn't quite like electrochemical oxidation. I mean, that's just applying positive potentials on,
Yeah.
versus something you could be oxidizing, methanol to CO2, or
Water to oxygen
I don't know,
gas.
water to oxygen gas. So, if you're doing research, so most potentiostats always have like 3 electrodes that are like leads. But if you're using like a power supply or something like that with like a sweep generator for CV, that would be the only configuration that's not a potentiostat, that you're doing that you have like only 2 electrodes, and you're able to, and you're doing research that way. So that's what I'm imagining or envisioning is the case, is you maybe are using a power supply to do research, because you say you don't have access to a 3-electrode system.
Yeah, it means you probably don't have a potentiostat or you don't have a reference electrode. Like,
Yeah,
you're right. I mean, one of the two.
and
So-
reference electrodes are relatively easy to come by. I can understand the potentiostat, but like people can make their own reference electrodes.
Yeah.
So if that's so if you have a potentiostat and you just don't have a reference electrode, you can do things to
Make
either make one on your own, but they're also usually very inexpensive.
Yeah.
So
Yeah, it would seem. I mean, I know that not everybody's lab and financial situations are the same, of course, and fair enough. But it's like, if it would seem to me logical that if your laboratory can afford a potentiostat, you could certainly afford a reference electrode.
mhm.
The other way around, maybe not so much, right? A potentiostat is just expensive, sophisticated piece of equipment. So, yeah, like you said, if you're working with a power supply of some kind, right, and you just don't have the sense line, of a potentiostat per se, then it's reasonable that you would be sort of stuck using a 2-electrode system. Really, what it means is if you're in this situation, there will necessarily be uncertainties and ambiguities as far as what potential you're at. You're trying to do oxidation. Well, that oxidation probably occurs, if you have a standard potential for whatever it is, occurs at E0 equals, point whatever volts versus NHE. There's some potential, right? And so you are required to sweep or apply a potential positive of the E0 to make it happen. And without a reference electrode, accuracies, I mean, you can call it whatever you want. I wouldn't really use the word accuracy. It's more like it's just the uncertainty of what potential you're actually at will make it tricky for you, for sure. Like, if you're trying to produce an oxidation reaction, you have to keep the potential higher than the E0. But if it's drifting around, it's moving a lot. I mean, are you going to be still applying that, causing the oxidation to occur? Maybe, maybe not. So yeah, I think you're going to be in a somewhat of a difficult situation. I would, recommend, if you can, to try to get your hands on a potentiostat, I suppose, and you'll have a little bit of an easier ability to know that you're applying the potentials you need to make the oxidation happen.
Yeah, I think we also need to know, like, I feel like I need to know a bit more about the system specifically, to really say, like, oh, maybe you're synthesizing, you're doing like a Shono oxidation of an alcohol, and it's like, oh, you're just trying to generate as much of a product as you can. Well, if that's the case, then go ahead. But when you report it, a reviewer may say, well, you need to report the potential versus
Right.
a reference electrode.
Because you might have the argument from a reviewer, or even yourself, if you're thinking about it critically. If you're just trying to produce a bunch of stuff, apply a high enough potential, measure the current or whatever,
Mhm.
Well, halfway through, if the potential is moving because you have no reference, your driving force for your oxidation reaction is changing, like actively, and you don't know what that is because you don't have a reference. So, yeah, it just creates a lot of uncertainty and I would say difficulty with analysis. So,
Yeah.
so possible, but you're going to be in having a difficult time to know what potential you're actually at all times, I would say. So,
Yeah.
right.
All right.
so
Next.
envious Praneeth, it looks like he has the same, but he sort of clarified.
Yeah,
the second
clarified in the
part.
second question.
So the question is, can we get the IV characteristics of solar cells like perovskite solar cell assembly using a potentiostat? Yes, you can. Using Keithley source meter is used to record IV characteristics. So you're using a Keithley source meter.
Usually.
Yes, you can use a potentiostat also.
Yeah.
I've never used I have used a piece of Keithley equipment once.
Mhm.
I can't remember what it was. Can't remember if it was in my postdoc or I just know the brand. I think I've used it. It was mostly like a power supply sort of, it's like electrical equipment, not necessarily electrochemical, potentiostat kind of equipment. But to get the IV characteristics of a solar cell, you can simply, you can use a potentiostat. You're going to connect the working drive and sense lines to one lead of the solar cell, and the counter and reference leads to the other lead, the other half of the solar cell, whatever you want to call it. And you're going to look for a positive voltage when there's light shining on the solar cell. So if you get a negative voltage, just flip the leads. That's basically it. Like if you have a commercial solar cell, they're usually like labeled, they're like red and black or something like that.
Mhm.
So red is the working electrode, black is the counter or the common, the other side. But if you don't have the sort of color coded leads, just connect your potentiostat or your source until you get a positive voltage with a light shining on the solar cell, so that you know that it's that's the open circuit potential of the open circuit voltage, whatever, of the solar cell, which is an indication of the maximum voltage that's possible, essentially, from the amount of light that you have illuminated. Then you're going to do one of two things. You're either going to slowly sweep the voltage down from whatever voltage is at. If maybe it's usually solar cells are usually like somewhere between 1 and 1.5 volts, something like that. So you're going to slowly sweep the voltage down from whatever 1 to 0. Or you can do a bunch of steps. So you could break up 1 volt into 1,000 1 millivolt steps, or if that's too much, a bunch of 5 millivolt steps, or 110 millivolt steps, whatever the amount of steps you want to do, and hold the potential at each of those steps for, I don't know, 10, 20 seconds, and get a steady state current. And then that's your like IV for that set of, for that voltage, that's the current. And you're just going to plot that. And that's your IV curve. So that's something you can do with a potentiostat. The nice thing, of course, is it's just more controlled than maybe with a power supply. In some cases, like you'd sort of just have a knob where you kind of like adjust the potential and you get a measurement. It's a little less accurate. You'll talk about accuracy. Potentiostats can give you really nice accuracy with this, more controllability about sweeping the potential or what are you doing. But yeah, that's a good way to get the IV characteristic.
Yeah, as a quick follow-up, I think you actually just mentioned this. It says using
Yeah.
LSV or staircase voltammetry. So you
Yeah.
already mentioned you could
Yeah.
use either one.
Yeah, you can use either one. What I described is sort of staircase voltammetry, I guess. I always think about it more manually, but if you do staircase, you can adjust the potentials, because that's exactly what it is. It's just potential, step the potential, measure, step potential, measure, step potential, measure, until you punch Alex in the face. Yeah, that's the same thing as LSV, really slow. In some sense, it's just the LSV is more smooth. It's digitized of a signal, but either way, you get a series of current and voltage. Yeah. So first record OCP. That's correct. then sweep from OCP to 0 using. That's correct. That's the quickest way to do it, right? With a potentiostat is measure the OCV, OCP, whatever. It'll be again 1 volt or something. And you can also get the OCV from a multimeter. Yes, you can. But with a multimeter, you can't get the IV curve because you have to be able to. It's like applying a resistor into it, basically, is what you're doing when you're using a potentiostat. So the potentiostat can lower the voltage and draw current out of the solar cell. So yeah, if you have to get the OCV from a multimeter and then plug that value into your potentiostat software or whatever, that's also fine. And then do LSV. Do it very slowly. Do like 1 millivolt per second is my suggestion. Do it slowly so you get a nice smooth kind of curve. It'll take a little bit, like 20 minutes or something like that, if you think about it, like 1,000 seconds, give or take. Okay. Go down to about 0, and then that's your IV characteristic.
There was a he just has a quick one. We can get the
that was what I was just talking about
OCP.
last. Yes,
Yeah.
you can get OCV from multimeter, but you could just do an OCV measurement with your potentiostat first. Then some softwares like in my company, our company software, you can like measure OCP. Then you can do LSV from LSV from 0 versus OCP to 0 versus ref. That's what I'm talking about. So 0 versus OCP is like 1.4, whatever the voltage is, whatever you're measuring. And then you're going to 0 versus ref, like you're actually going to 0 volts is the maximum current that you can get out of the solar cell. That's effectively a short circuit. 0 volts between the anode and the cathode, or either side of a solar cell, is effectively short circuiting. You're having a 0 volt. There's it's like a ZRA measurement, basically. It's basically the same thing. So those are the two extremes of a solar cell, basically. There's the maximum voltage at 0 current. That's the OCV. Under some set of illumination, right? Exactly, the settling period. You got to make sure you have your settling period. That's thank you. Welcome, Tarek. So the maximum voltage is the minimum current, and then vice versa. The minimum voltage, 0, is the maximum current you can get, and so the IV curve is the connection between those two things. Settling period. Join my webinar on Wednesday. I don't even think I mentioned the settling period one time. You're going to be very disappointed. I know it's very sad. All right, let's see, where are we at here? I know we've got some follow-ups from Joe. He's going to look at.
For me, he's just asking, do you have a vendor in India? Yes. So you can purchase stuff. Batsol.
Yeah, I'll pull up the website just to show you, but they're called Batsol. They have offices in Mumbai and Kolkata. Let me pull them up and I'll show you. So if you come to our website here, I'll just share my tab here. This is right on our website, pineresearch.com, and the sales channels up here. You can see there's a map. So if I just click on India, you see Batsol will come up, and their contact information and website is here. So you can contact them, and they can give you quotations or anything that you need for India. Okay.
All right. So we're just kind of going down the list of the order with which we receive questions and comments. Joe already told us about potentially pushing the potential to hydrogen and oxygen. And it looks like Amit is next. Amit's asking, I'm doing research on MOF synthesis and application for, I guess, water splitting play a pivotal role in this. Can you tell me about EIS? I asked him for a little bit more details, but specifically he wants to know about the EIS graph use in application of MOFs. So typically, just describe a little bit about EIS application in MOFs. So let's just start. So most of the time when people are doing EIS, you're looking at there are two types of plots. There's a Nyquist plot and a Bode plot. The Nyquist plot is the more common one, where you're measuring the negative imaginary impedance on the y-axis and the real impedance on the x-axis. And of course, as you're doing EIS, you're doing this at a bunch of different frequencies. And typically you end up getting these kinds of ideally semicircle looking things. You may have a Warburg tail. You may have multiple semicircles of varying sizes. You might see some stuff that looks like that. When people are studying MOFs and you're synthesizing MOFs, those MOFs typically exist on an electrode, some kind of substrate. So you're going to have some electrode material, and then your MOF, maybe I'll use a different color. Your MOF may look, something like this, right? It's just something that's on the surface. And so typically, and granted, I'm not an expert in MOF chemistry or EIS of MOFs, but typically for any electrochemistry experiment where you have an electrode, some kind of material of interest, in particular, you have a MOF, and then you have your solution with kind of maybe some kind of redox species, CB. You can study reactions. You can understand things about charge transfer resistance, the capacitance of the MOF. It may be able to give you information about the porosity of the MOF. That's also a possibility. You may get different shaped impedance spectra based on its porosity, but usually you do some level of circuit fitting. So maybe you model this as a leading resistor, charge transfer resistance. Maybe there's some kind of capacitance or CPE. I mean, maybe there's another layer of this. Maybe there are multiple processes that are occurring on the surface, and these values correspond to certain aspects or certain semicircles in your EIS, and that'll tell you some information about the capacitance of your MOF layer, or sometimes the Warburg element itself here will also tell you information about porosity, because maybe the MOF film acts as though it's a porous electrode, and only certain chemicals or materials can fit in the pore of the MOF that can get to the electrode structure to actually diffuse and do some kind of electron transfer or something like that. So there's a lot. You just asked me like, how does an EIS plot relate to MOFs? And there's a whole bunch of things that could be the case. And I think MOFs, what was it? The Nobel Prize in chemistry was due to MOF chemistry. So
was
I'm
it
not,
really?
yeah,
Oh, that's
yeah.
cool. I didn't know
But I don't. So I might not be doing them a really good service by actually doing that. I should probably talk to some people I know from graduate school who actually study MOFs, and they'll probably know a lot more than I do. But hopefully, that kind of gives you the gist of how EIS could be used to study MOFs. And if you have further questions, you can try to answer them.
I don't have a lot of knowledge of the metal organic frameworks, unfortunately.
Yeah.
So I have nothing to add. But I can try to help the POC friends who says, I want to know about electrochemistry and its application in the research fields. Suggest any reference from where I can begin for my basic understanding. Electrochemistry application in research fields is primarily in batteries right now. It's probably the most common and most popular application and the most relevant one. I mean, consider every virtually consumer electronic device in the market all around the world uses batteries, primarily lithium-ion batteries. Most electric cars use lithium-ion batteries. There's a lot of research on sodium-ion batteries and other kinds of batteries as well. And that is all electrochemistry. So virtually the entire power source for like all of the world involves electrochemistry right now. So it's very, very relevant. In addition to that, you have things like biosensors. Screen printed electrodes are used for like detection of various contaminants or things of that nature for medical or biomedical devices. That's one of those. Another application. Fuel cells and other energy. So batteries is an energy storage device, but capacitors, supercapacitors.
Semiconductors.
Semiconductors. Oh yeah, Matchaki.
Matchakis.
Come
Keep
join-
talking about it
Come
later.
join. I'm like a
Next-
meteorologist, right? Like trying to point to the green screen.
Yeah, or you could just
This
you
guy
could just
right
do
here,
this.
talk about that stuff right there. Then there you go. That was pretty good. That's like there's a rain event coming in here, and you can see over this area of the country. I don't know
And
how-
luckily, you don't have to point to something that's like super specific. It's like, we got a cloud formation that's in this area. It's like,
yeah,
luckily, clouds aren't like this big,
yeah,
and
tiny.
you have to like point to it
I have
very
to like
carefully.
point to like this capacitor right here. Anyway, so capacitors, semiconductors, fuel cells, solar cells. These are all electrochemical devices as well. So there's probably some more, but I'll just sort of leave it there. Those are some of the more common fields that are using electrochemistry research and basic understanding. Well, unfortunately, I think the real answer to that is to be in a research group of some kind, either at a university or a company doing R&D, I suppose.
Mhm.
The basic understanding of electrochemistry, broadly speaking, can be done by some textbooks, like Bard and Faulkner textbook is the most famous example, and of electrochemical methods and applications, and just electrochemistry as a discipline and a subject. And then reading literature papers of whatever field specific, sub topic, like again, batteries, fuel cells, whatever it is. You can read some of the scientific literature and see what people are publishing and doing. But for like research, like that's sort of fundamental electrochemistry, and our shamelessly our YouTube channel here, we have a lot of videos on both of those things, on cyclic voltammetry and impedance and how potentiostats work. And this live stream is 116 some odd episodes of us just answering questions for 2 hours. And there's timestamps in every one of them, so you can search through timestamps. And how many people have asked about taffel slopes? It's like, well, the answer is a lot, but you can find a bunch of answers and questions on our YouTube channel. We try to be a reference for this exact reason. But the ultimate answer, really, if you're like trying to learn electrochemistry research and like how to do it, what it is, just all that kind of stuff, the answer is getting into a research lab and just having access to those things. So unfortunately, if you're someone who just has an interest in this, but you're not in university or in a place where you have a potentiostat in a research lab and chemicals and all the stuff that you need, frankly, it's not going to be very easy to learn about the research if you can't do it, right? Because research is really one of those things that's you learn by doing and failing, over and over again. It's just one of those that's the nature of it. You really have to get your hands dirty, so to speak. So. Okay, let's see.
All right. Oh, Tarek became a tier 2 member. Thanks, Tarek. We appreciate it.
It took a long time because he had a long settling time before he got there. There was like 5-year settling time, but then it ended, and so now he could become a tier 2 member.
Yeah, he could become a tier 2 member.
Yes.
All right. Okay. So
okay, we got Pranit's questions. Ibrahim, I think, is next.
yes.
Okay.
But I don't know what Ibrahim's asking. What are the overpotential that is frequently reported for AEMWE? And I don't.
Anion exchange membrane working electrode.
Oh.
But I don't know what you mean by overpotential that's frequently reported. Do you mean like the state of the art, like the benchmark, or what's the current benchmark? Because if that's the question, I don't know the answer for that specific application. Yeah. For an AEM fuel cell or working electrode, whatever, I assume that's what that means. AEM stands for alkaline exchange membrane. So like AEMFC is like an alternative to PEM fuel cells, proton exchange.
Mm-hmm.
So it's like a fuel cell where hydroxide is the carrier ion instead of protons, something like that. Or just any other anion instead of a positive proton, charge,
Mhm.
being the ion moving through the membrane.
Okay.
Um,
So it's alkaline exchange
so it's
membrane.
alkaline or anion. Yeah, it could be either, right? Alkaline
Okay.
if it's hydroxide, that's most common, I think.
Okay.
But it could be anion. Alkaline, like hydroxide, is
So we just
okay.
wants to know
State of the art. Honestly, I don't know. I mean, that's just something to look up. I don't know off the top of my head what it is. You know, like
Yeah.
what is the benchmark? Actually, my group that I went to graduate school, when I was in graduate school, we worked on alkaline fuel cells, and I believe so. My advisor is Bill Mustaine. What was Bill Mustaine? He's now at the University of South Carolina. To give him a shout out there. I believe sometime in the recent years ish, his group. I've been out of that group for a long time, so it has nothing to do with me. But his group has developed some alkaline anion exchange, catalysts or devices or something with close to state of the art, or like they hit some benchmark. Like, again, I'm speaking not specifically here because I don't know the answers for these, but like it's usually like this many watts per centimeter or something, or centimeter squared or centimeter cubed or something, or this many milliamps per centimeter squared. Like there's values for those that are like the US Department of Energy will often put out like goals, like target goals for performance of a fuel cell. I don't know what these are. Like, I'm not in academia, so if you're in academia, you probably know these. Like the goal is 500 milliamps per centimeter squared or something at 50 degrees Celsius, and then like every group is trying to meet that, and then they increase the goal once it's hit. Like those are things that happen, and if you're asking me what the number is, I just don't know. I don't. You could probably look it up. I could probably look it up. If you have a question about that in some other way, I can try to talk through it, I suppose. But if the question is like, what is the benchmark at the moment? I honestly don't know. I'd have to look it up. Like, it's probably for the US. I mean, it might even depend on the country. I have no idea if these are international or like specific. You know what I mean? Like the United States, we have our own sort of Department of Energy and Science Foundation metrics and goals, right? For instance, and they change or they go up over time, and so I just don't know what those are off the top of my head. Unfortunately, I don't know.
Yeah, I don't know either.
Yeah. So hopefully that kind of, I assume that's what you're talking about, and like I said, if you have a more question about some part of that, I'm happy to talk through it. But otherwise, that might just be something you can look up. Some tabulated number somewhere.
So Jesse Mentors next. He's asking, I've done LSV for sodium symmetric cell, and I've measured the OCP after, and it doesn't come to the same value. What would be the cause of the OCP before and after being different? And so let's see. So he has a symmetric cell.
Symmetric cell.
I've measured OCP after, and it doesn't come to the same value as before. Before and after what?
An LSV, I guess.
Oh, before and after an
Sounds
LSV.
like, yeah, so he's got like OCV. He does an LSV, like he moves it around, probably up or down or both or something.
Yeah.
And then when you reset, so to speak,
Yeah, then we take
the
OCP
OCV
again.
isn't exactly the same.
It's not the same.
It's not surprising, to be honest.
Because you did an LSV experiment.
Yeah, you did something. So you did something to your electrode. So two things. One of them is that you actually did something. I know you say, well, it's symmetrical cell, so everything I did to one is like the opposite of the other. Like, you feel like you're not doing anything because it's symmetrical cell, but like you adjusted the potential, you caused current to flow, you caused some reactions to happen on both sides, maybe not exactly the same way. So something might change, which means that the thermodynamic open circuit potential will, just no guarantee it's going to be exactly the same. And then the second part is just to say that it's one of these things where you're like, well, here's my situation. And my answer is that that's not your situation. And so what I mean by that is you tell me this is a symmetrical cell. I have the same electrode on both sides or something of that nature. And my answer to you is no, you don't. You actually don't. Like they're not exactly the same. They're not 100% precisely the same. There's something probably ever so slightly different about each. Well, I know they're both like sodium metal, right? Okay, so it's probably the same material, but like the surface condition or the mass of each of them isn't exactly the same on both sides. It's not 100% exactly the same. It's just not like that's electrochemistry, right? There's just slight differences, impurities, and other things. And the open circuit potential is, some aggregate of the thermodynamics on either electrode. And if you did it a linear sweep, you swept around, something small changed, and then the OCP will be different. Like, I don't know.
But isn't it the case that when you do LSV of a battery, right? This is a battery.
I assume so.
Because he says it's a symmetric cell.
Mm-hmm.
Then you've always said you don't want to do CV or LSV for batteries because changing the voltage, because you're sweeping the voltage, means that usually you're pushing a tremendous amount of current.
Yeah, it depends how fast he went.
But even if he's going very slow, it can be pushing a tremendous amount of current.
Yes,
possibly.
That's true.
So if you're pushing a tremendous amount of current and you have lots of charge buildup on one side and less on another, then it feels like it wouldn't be surprising that the OCP is different. We also don't know how much the OCP is different from one to another.
Right.
So is it a 50 millivolt difference? Is it a 1 volt difference? I mean, that'd be kind of crazy, but
to your point, actually, it's a very good point. Even if you scan kind of slowly, you could have a tremendous amount of current being passed. And what that means practically is that one side had an oxidative current, the other side had a reductive current. Those are going to be different things. Now, maybe it's some part intercalation and deintercalation, because it's sodium. Maybe it's just sodium battery. Like on one side, it's Na, plus an electron goes to Na solid or something. And the other side, it's Na solid oxidizes into Na plus and an electron. So maybe that's like the most simple reactions that are occurring at both sides. But if there's a huge amount of current, you could have other reactions occurring as well. You could have electrolyte. I don't know if sodium batteries have SCI, like a lithium battery does that, but you could have like some film formation. You could have, some reactions occurring with the electrolyte. And if one side has an oxidation and the other side has a reduction, those are different. Like something might reduce on one side that's different than an oxidation on the other side. And it produces some film or transient or I don't know, something could be occurring in this scenario. And so, yeah, it's not surprising. Let me put it this way. It's not surprising that the OCP is going to change a little bit because of everything we just talked about. But that also doesn't necessarily mean that there's anything wrong. Like the OCP could be different if you have like a very minute amount of something there, because the potential isn't really dependent on like, if you have a like 10 meter square meter sized electrode or a 1 millimeter sized electrode, it could have the same potential, like in theory. So my point is, like, if you have a very small amount of something that got formed because of this, it can affect the potential. But
so I guess let me ask a question, because I feel there's a part of me that feels like if you've done LSV, it's obvious that the OCP should change, especially if you have a battery, because when you do LSV, you're either charging or discharging the battery in some capacity, right?
So yes. The only follow up to what you're saying is that let's just say in theory, what he did was go the same distance in both directions or something. So
but if it's LSV, it's only one direction, right?
Oh, well, that's
Jesse?
That's true.
You said LSV. You didn't say CV. You said LSV.
That's a good point.
I'm gonna grill you on this. But if you said CV, it's like, all right, well, maybe
I was thinking CV. I think you're right.
Maybe,
so if you did LSV, that means you
only went one
charged
direction.
one side and discharged the other side. So you actually did change, like, structurally and morphologically, both sides.
And the potential will be different.
The potential's going to be a little different.
And the OCP is as if, if you took if it had a battery and then you measured its voltage, just with a multimeter, which is what OCP is, and then you charged it, and then you also measured the OCP, you'd see a difference.
So that the counter to that, if there would be one, would
Mhm.
be something like, okay, but both sides just did the same reaction, which I don't think, again, I just
Right.
explained why I don't think that's the case.
Mhm.
But let's just say, for argument's sake, both sides just did the reaction of either taking away or adding sodium. And so that compositionally, nothing really changed.
So you think, what
Hey, our
happened to-
background went away.
Your background went away.
This happened before.
No, you can't see it.
Can't see the
No,
green
you can't
screen.
see the green screen.
I don't know why that happened. That happened before. Anyway.
That is weird.
So, but my point is, like,
Yeah.
okay, so compositionally, it's still both sodium on both sides. So it's
But the potential, so you can have two silver chloride reference electrodes and measure a different a different potential between them, because the composition of the chloride ion between the two can be different.
Yeah.
So and no different. It's like, if the concentration of sodium ions is something on one side and something else on the other side, you're going to get some kind of voltage difference because of the Nernst equation.
Yeah. The Nernst
I
equation.
got a chance to say it.
Hey, look at that.
You'd think I might, I get away with, I wouldn't get away with
No.
it, but
It didn't even take that
it
long
didn't even take that long
to get to the Nernst equation.
So that's what I think. Okay. All right. Wait. All right. Jesse has a comment. Let's see.
Yes.
I went from 0 to OCP. That makes sense. So should I do CV? Okay. So now he's asking if he did CV.
I don't know that it's a should anything. I think,
Yeah.
Are you like dead? Like, what are you trying to learn?
Yeah.
Right. That's the question.
Ask that question.
Is it like a big deal that the OCV changed? Because everything that we just described explains why it would change.
Yeah.
So it's like, okay, there's nothing wrong with it. Like there's not even necessarily anything wrong with your electrodes, your setup, anything. You're just discovering a normal, consequence of chemistry here. Like I don't actually think anything is wrong.
Yeah. Yeah.
Right. So,
like you, it's like you did a thing, and it's like, is it good or bad? It's neither good nor bad. It just is.
Yeah. This is just science.
This is just
you just did science.
Yeah. I mean, I'm also of the opinion sometimes, like, we try to associate like good and bad to certain things, and it's like, well, but if you were trying to do the thing, then maybe there is no good or bad. It simply is. You just got a result.
Hey, look, I got the green screen back.
You got the green screen back on.
But I put a meme up by accident.
No,
I'm gonna put my thing back.
I wonder why the green screen.
I don't know. This happened before too, and it's a very weird thing. It happened like, it wasn't even live. I was practicing something and it went away. I was working on my webinar or something and it went away. I'm not sure. It's very strange. Anyway, it's back.
Report that.
So
anyway,
I didn't have to cancel. So
okay. So let's see.
The next step of my experiment should start from the OCP and then move up again. So that's what I was going. Okay, yeah. So So your choices are, in theory, if you were to do a CV and spend, which this is tricky because even that isn't necessarily going to work exactly as you think. But in theory, if you spent exactly the same amount of time at a positive as a negative potential, you might retain the same OCP, over time. Possibly. You may not, but okay. And there's other things. There's IR drop and stuff that are going to, impact this. So, but let's just say you really are adamant about keeping the OCP like at the same rough position from test to test, experiment to experiment. Then, yeah, possibly doing CV. Everything sort of symmetrically with your symmetric cell, you might hang on to your OCP. Alternatively, just measure it frequently. Like after every step, have a additional step where you recheck, remeasure the OCP, and move everything, like adjust it accordingly, right? Like if it's step 1 is do a thing, step 2 is do a thing from OCP, right? And you measure OCP at the beginning. Well, you might have to also measure OCP after your first thing. So just measure it, and then if it did move, okay, no big deal. Just adjust your next thing based on the adjusted OCV and move on, and you'll probably be okay. So I think that should be should. I mean, it should work in theory. So yeah. But good question.
Yeah. All right. So if we go back, Ibrahim has another question, I think slightly different, which I think we might need some additional clarification on. But what can you say about CV of a carbon coating from 0 to 1.6 volts, a peak at 0.5 volts versus NHE? The CV was done 4 times with the same peak without decreasing at same potential, no reduction peak, and it was at a scan rate of 50 microvolts per second, which is extremely slow. Those are long experiments.
Could be an EC reaction.
EC reaction. Oh, well, yeah.
Like you're scanning so slowly that if you have an oxidation peak?
I think
No
that's
reduction
usually
peak. Yeah. So if you have an
same
oxidation peak, maybe you're forming some species that then like is by the time, next week when your scan returns, like it's taking so long, so much time has gone by that the thing that was formed on the forward scan is no longer present. It's been reacted away. So you don't have a reduction. It's an irreversible reaction of some kind.
Yeah. I'd ask some more, like, also it's like, well, what can you say about it? It's like, well, it's a carbon coating. I mean, it's not like you have a glassy carbon electrode. You may not have something that's like very pure. It's possible that I think about our CVs because there's occasionally humps and oxidation things.
There's usually a little
carbon.
Oxidation, like a little. It's actually reversible. There's a reductive wave, and on like glassy carbon, around like 0. I guess it depends on the reference electrode and stuff like that. But like around 0 versus in some conditions, like when we do our like factory testing, for instance, of our like glassy carbon electrodes that we sell, you'll see a small wave around like 0 per se. So let's just say if you add the reference electrode potential to that, it's probably like 200 versus NHE, something in that range. So we're close to what you're saying. But we scan at, I don't know, 50 millivolts a second or something. And usually there is a reductive sort of wave on it. And I think it's just a small oxidation that occurs on the carbon. It's like some oxidation, some oxide species. It's a normal thing you see on carbon. Otherwise it's relatively inert.
And I'd also ask, what is the scale? Like, what's the y-axis? It's like, I got a peak, but I got all 50 picoamps, and it's just like,
well, that's not it.
It's like no.
Is it a really small peak or is it a big peak?
Like, is it a big peak or is it a small peak compared to other features? It may be something. It might be nothing.
It could be nothing. I think that's true.
So that's the question. I
think the only other thing we can say though, like with definitive, like knowledge, without, as I said, definitive knowledge of any of these details, is that if you have an oxidation peak and no reduction peak, it indicates an irreversible reaction.
Oh, we have another detail.
Is there a
Okay.
detail?
He said, I scanned at 200 microvolts. The peak was invisible. Hence, I tried a much slower scan rate. Interesting. So when he moves to faster scan rates,
it's not there.
It's not there.
So it's a really slow reaction.
Or it's happening, or it'd be weird. Double layer capacitance is like overcoming it or something.
Yeah. Like if the peak is so small that when you scan faster, even at 200 microvolts a second, which is really slow.
It's still very slow. You're
still going to have a double layer form as you scan. That the peak. So like if you would imagine, for instance, if I can draw, it's a big if you're scanning potential,
so slow.
So if you have your CV, just draw it like this or whatever, and if you're scanning at 200 microvolts per second, which is really slow, but I'll just pretend it's sort of not insanely slow. I'm just going to draw everything up here. It might be around the around the 0 axis, but I just want it to be a little more visible. So let's just say I scan, I kind of get something like this, right? I'm just drawing it with like no features. So just bear with me here. But you can imagine basically this like window here, and it's probably actually almost overlapping when you're scanning that slow, but if there's some window, this is like you know, the double layer capacitor like is responsible. I know it's half of that, but you know what I mean. It's basically that's where you're seeing it. So basically, if your peak is really small and you're only going to see it if you like your peak should be, you know, halfway through. It's like if you scan at what was it 5 millivolts per second? What was it?
50 micro
50
volts per
microvolts, 50
second.
micro. Okay, so if you scan even slower, so you cut it
Yeah.
in a quarter, 50 microvolts per second, your double layer is going to be smaller, and so now it's like you'll finally get to see this peak. Let's just say it's something like that, right? And there's no corresponding oxidation, something like that. Like it might just be that the peak is so small because it's almost insignificant, but it gets swallowed up by the double layer if you're going fast. That could be it. It could also be, I mean, I guess, right, if the kinetics are like really, really slow, you'd have to scan slow to see it. Would that be right? Is that possible?
If the kinetics are slow, it usually just pushes it out the window with which you see it.
Oh
like
yeah,
from
that's
an
not going to
overpotential
necessarily mean you
perspective.
won't see it at a fast scan rate. I guess if the kinetics are so slow, like, I mean, like over a week, painfully slow, you know, like,
This is painfully slow.
yeah, like in theory, at a slow scan rate, you wouldn't see it, but that's like kind of ridiculous. I doubt that.
So
maybe
I
that
would
is.
also, you know, Ibrahim, for your own sake, I would just try a normal differential pulse voltammetry experiment.
Yeah, that's
A
good
technique that's designed, or even square wave,
idea.
but a pulse technique that's designed to remove background Faradaic current, and that if there are weird features, really, really tiny things, little tiny peaks in your signal, they're amplified, sort of say. You're able to see it more clearly. So I'd recommend doing some type of pulse technique, primarily differential pulse. And if you're worried that you're like not going to see the signal, you know, of the parameters to adjust, I would change the amplitude of your pulse. But that's to be done later.
So I'll share a couple of resources with you to your point.
Yeah.
So this is differential. If you're not familiar with this technique, this is on our website, our support page. Differential pulse voltammetry waveform looks like this, right? So you go up, down, that's the pulse. And the one that Alex suggested changing was the amplitude. I wonder if we have a lot of, there's a lot of
yeah. So it's the
this
EDPH.
Yeah, this
you want that
brown
to be big.
positive. You can see my mouse. Yeah. So
yeah.
so this one. So you can adjust that and see. But basically, what you're doing is like if you pulse up to where the peak is, and then you pulse back before the peak, you're subtracting the measurements. So that if you pulse where there's no peak and you subtract the measurements, it's zero. So what it is it clarifies the peak for you.
Yeah.
Everything is basically zero baseline, even if there's double layer. And if there's any peak or change, you get a response.
Yeah.
Okay. And then the other thing to share you is that this guy to my left here did a webinar series covering exactly this topic. So I'm gonna show that.
Yeah.
The last of your 4-part voltammetry series, which is on our webinars playlist, covered differential pulse voltammetry in a lot of detail. So this one in particular, so I'm pulling it up now. I know it's taking me a second.
Yeah.
I got it finally. Okay. This webinar here, and I'll link to it in a moment. Voltammetry series part 4. Okay.
Oh, that was me. I was.
That was
like,
you
talking.
You talking on the video. That's
on
right.
the video.
Yes,
okay.
Yes. So I'll just go into the entrance, whatever entrance screen here. So so you see, this was a webinar Alex did about a month ago or something like that, right?
Yeah.
Voltammetry series, and I'll link to it. So you have to be a tier 2 member of our YouTube channel to watch it, but there's a lot of information there.
Yeah. You can just be like Tarek, who just became a tier 2
That's right.
YouTube member, and if you're like Tarek, TGGZ, you'll be able to watch it.
You can watch all the voltammetry that your heart can handle.
Yeah. You
So-
watch EIS. You can also watch all the other, there's like a lot of content on, and we're going to be adding more.
Right.
Relatively
Like my
soon, too.
upcoming Mott Schottky webinar.
Will eventually be on
It will
that
be
as well.
in there as well. So
Yes.
yeah, hopefully that helps Ibrahim give some of that a try. All right, where are we at here? So they jump around a little bit, but verses of gold.
Yeah, verses of gold.
Oh, I see. It's just a comment on the.
It's just a comment.
Yeah, there's surprisingly very little textbook literature in semiconductor impedance. Interesting.
There's definitely good papers.
I guess you might be right. I mean, honestly,
Not so sure.
I'm not positive. I don't know of any either, but I'm doing a webinar on semiconductors on Wednesday, but I'm not really an expert per se. I didn't do a ton of semiconductor, research, I guess.
Yeah.
So, Mott Schottky usually finds its way into textbooks, but not as the subject of a textbook, I would say. So you're probably right. Mott Schottky and semiconductor electrochemistry in general is usually like part of a text on electrochemistry or impedance in general, right? It's not the subject of a book by itself. Tends to not be.
All right. Well, Ibrahim actually took our advice. Thank you
Wow.
for coming to Tier 2 YouTube member.
How's that for marketing?
That was fast. Yeah.
Yeah.
And of course, let us know if you have any questions about that. But differential pulse, you'll learn a lot, and you'll also learn more about CV and other things too. So we hope that you
so
find it
much.
very
We appreciate
valuable. Yeah. Your support, everybody's support as a member helps keep this kind of content running.
Yeah. Keep it. I mean, the webinars are for Tier 2 members, but when we do them, they're free.
Yeah. We want to try to create as much free stuff.
This
too.
webinar is free on Wednesday. You can register on our website, and watch it live for free, and it'll be there for a couple weeks for free, and then it will join for the Tier 2 members. So we appreciate your support. Santiago, I think, is next. Okay, so Santiago says, in supercapacitor applications, how do you differentiate between two EIS spectra to determine which is better than the other? The simplest way would be to do a fit, find the capacitance measurements, and find which one's bigger. Like that would be the simplest possible answer I could give you. So, you might, for example, have two supercapacitors, and they give you spectra that are like, they don't look like anything just at a quick glance. Like you have spectrum 1 for like the Nyquist plot, for instance, and like spectrum 2. And spectrum 1 is like, ooh, it's a big line. And spectrum 2 is like, you're never going to believe this. It's also a big line. And it's like, which one is better, right? Okay, so all you're going to do is basically fit like the simplest, like this is like the simplest possible what your data looks like, and your data may not look like this. You might have like, you might have a Warburg element, or you might have semicircles, you might have all kinds of stuff. You might have 3 inductive loops in a row, or you might have none of that. So I'm being a little ridiculous, but my point is, if this is your sort of simple circuit, diagram, you're going to fit it with something like a resistor and a capacitor. Like that would be the simplest possible option. This is just some like ohmic resistance or uncompensated resistance, and this is your capacitor. So this is the one that you're interested in. You could also fit a CPE if you want instead, if it's non-ideal. So that's just an option. You can fit a CPE if you like, but the simplest option, of course, is to fit just a capacitor, and then it might be not ideal. That's fine. The point is, whichever capacitor in theory is bigger, whichever capacitance in farads and microfarads, millifarads, whatever the number is, would in theory be the one that has more capacitance, which is better, right? It's holding more charge. It's a better supercapacitor. Mm-hmm. So that would be my suggestion. If you have a follow-up question, like, oh, well, actually, this is what I'm seeing, or do I, there's other considerations. Certainly those can come into play, but as the quickest possible answer, that's probably what I would say. Very, very, very simply.
Yeah. That's good. Let's
see.
Yeah, we have a new question that came in.
Mm-hmm.
I don't know if I know what the answer is, but TA1R8A is asking which corrosion prevention method involves coating iron with a layer of zinc that corrodes before the iron does.
Oh,
I don't know what it's called.
it's like a sacrificial anode.
That's just the it's just like that's the method that we would sacrificial anode.
I mean, that's something like that. I don't know if that's
Yeah.
exactly what it's called, if it's the same thing. But yeah, this is a cool thing. I don't know. Does it have a name?
No,
I
yeah,
feel
I
like
don't know what the name is.
sacrificial something has been a term that's been used for things like this, but you're taking advantage of the Nernst equation, actually.
Yeah,
The thermodynamics, right?
Thermodynamics,
The
mostly.
potential. The potential. I mean, I actually have to look it up, but
Yeah, it just it has
standard potential table, like zinc has a more favorable.
oxidizes-
Yeah, exactly.
Oxidizes at a higher potential, so more thermodynamically favorable than iron.
Yeah, I'm trying to look it up to see.
Oh, Barris is saying galvanization. Is it called? Is it
that what it's called?
called galvanization? I
Might
mean,
be. So iron 2+.
I think that's
so iron oxidation occurs
yes, galvanization.
positive of minus 0.44.
Yeah.
So zinc occurs positive of probably more negative than that, it would be my guess.
Okay.
Yeah,
So
that's right.
So
So minus 0.76. So it's like if you could be
right. So
you could be negative of the iron potential, meaning it's preferring the reduction, which means it's not going to oxidize.
That's negative of iron, or
okay. So here's a way that I think I can explain this: galvanization.
Well, yeah. So that's that's the
minus point
corrosion prevention method, what we would call it. Okay.
And why it would work.
Yeah.
Is if you have a number line. So this is a potential number line, right? Or like an E0 number line. Let me get my numbers again. I have it in my tab here. So minus 0.76 and minus 0.44, I think are the numbers. Yeah. Okay. So minus 0.76, that's zinc oxidation, and then minus 0.44, which is more positive than that, is iron. Okay. So what this means is that in this zone here, we're happy. Nothing is oxidizing. In this region, negative, roughly speaking, right here. That's negative of the zinc and of the iron, right? So negative prefers the reduction reaction. That's not corrosion. Corrosion is the oxidation side. So basically, if we're super...
And the way you've written this is that reduction potential represents the reduction.
The reduction, that's correct.
Okay, reduction of zinc.
So in this region here, this is where the key is. This is why it works, right? In this region right here, zinc will oxidize, but iron won't. Right?
Yeah.
And in this region, everything we're sad. Everything is oxidizing and rusting and dying. Yeah. Both of them will. But it's this middle region here, which is why this works. Because in this potential region between basically minus 0.76 and minus 0.44, zinc can oxidize, but iron can't. And I say can't. You know what it's not exactly the case, but I'm just being simplistic here. Yeah. Because the iron will really only do the oxidation mechanism if we go positive of its potential. The other way to look at that is that if I'm at any potential, the driving force for zinc is greater than the driving force for iron.
Yeah.
That's the other way to look at this. Yeah. So whatever the potential happens to be, if I'm at potential is equal to minus 0.2 volts, that means that my overpotential for iron is 0.24, right? Is the math? Did I do math right?
So you're saying
like the overpotential for the oxidation is 0.24.
Oh, okay. The overpotential for the oxidation.
Yeah, for like iron oxidation is 0.24
volts. Oh, okay, sure. Yes.
However, the overpotential for zinc oxidation is bigger, right? It's 0.56.
Yeah. So zinc has a higher.
Right. So
Uh,
so the overpotential for zinc is higher than the overpotential for iron. So there's a bigger driving force for zinc to occur, which means zinc is going to happen exclusively or at least faster.
mhm.
And then once it's all gone, then the iron will start to oxidize. But
Yeah.
you're taking advantage of this thermodynamics.
Yeah.
And so I guess it's called galvanization, or it's a you'd call it a sacrificial, you know, sacrificial something like sacrificial anode or sacrificial metal. I'm not sure precisely what you would call it, but yeah, that's a cool like way to take advantage of electrochemistry, basically.
Yeah.
I think, yeah.
Standard potentials.
Yeah, exactly. So nice.
All right. So we have so Mahesh has a question.
Looks like it's copied from a test.
Yeah, but it's a weird question, just because it's in parentheses. But it's
Mhm.
but the question doesn't make a lot of sense because it says in potentials many occur in practice. Why? What do you mean in potentials?
In potentials.
In potentials many occur in practice. Why? Discuss the thermodynamic and kinetic factors that limit the predictive power of standard electrode potentials. So, thermodynamic and kinetic factors that limit predictive power of standard potentials. Oh, like why is it that? I mean, well, we just demonstrated that the standard potential does have predictive power. Like you can, like you can galvanize iron with zinc as a corrosion inhibitor.
Yeah.
Purely from
The predictive
from
power of
thermodynamic.
standard electropotentials.
Yeah. But okay, so if
So
we want,
the kinetic factors that limit it would be that if the zinc speed is super slow, then the iron one might still happen. So that's one way to look
correct.
at this.
Yes, yeah. So there is the so yes, kinetic factors definitely limit. So thermodynamics states whether or not something fundamentally can happen, and kinetics tells you a little bit more about the rate at with which that process can occur. And so it's like given infinite time, then then thermodynamics will win. But kinetic wise, that's why you may observe overpotentials, right? It's because kinetically, it's difficult for a certain electron transfer to occur. And in my opinion, Marcus theory perhaps gives you the best conceptual understanding of thermodynamics, or sorry, of kinetics. You know, what affects the rate of an electron transfer for at least simple systems. But yeah, it's like, can you get all the atoms in the right orientation for the electron transfer to occur? No, it's kind of hard to get them there. Well, then that reaction is going to be slow. It's going to have slow kinetics. Conversely, if the molecules that are undergoing the electron transfer don't have to move around that much, well, it's really easy to have electron transfer. The kinetics can be very fast, and then it's purely a thermodynamic thing. So, Mahesh, if you want to give us more details about like exactly what you mean or explain more, I'm not really so sure because the first part of the question, in potentials many occur in practice, I don't know what that means. So if you want to elaborate a little bit more on that, or if you just want us to talk about thermodynamics versus kinetics and the power of predicting standard electrode potentials, you can usually, standard electrode potentials are determined experimentally, but they usually follow relatively simple electron negativity principles from like the periodic table. Ionization energies, I mean, they typically follow those pretty well. You can go down the periodic table. The reason why like lithium and sodium ions are being used for batteries is because of their potential and their ions. And guess what? They're both in the same column in the periodic table. But because of their size and their chemistries, there are some differences that are important. But they basically, most of them follow periodic table trends, if you want to think of it that way. So that's another like kind of helpful thing. So I don't know if you want us to elaborate more on that, we can, but this isn't really a. It's a very broad question. That's not even that. The first statement, the premise in potentials many occur in practice is a little odd. So that's kind of throwing me off.
Yeah.
For answering this question.
Yeah, it looks like it was lifted from, some online exam or something of that nature. So it's, I don't know.
It's not a good online exam because it says in potentials many occur in practice.
What does that mean?
What does that mean?
It doesn't mean anything.
Maybe this was AI generated.
Could be AI generated. Could also just be out of context, something bizarre.
Because AI, what is it? I heard some teachers are using AI to create questions, and it's just like,
yeah.
So it's like, it's not the students who are having issues.
No, but it's both.
It's both.
I can tell you that I know for sure. This is a both thing. There's a lot of students that are like using AI to try to do their entire homework and their entire coursework for them, and it's a travesty. And there's a lot of teachers that are also doing it. Like there's a lot of like teachers, there's like supervisors, there's like people in positions where they have to like I'm speaking very generally because I'm not outing anybody in particular, but I could, but I know somebody who, for example, had evidence of a supervisor or superior who had to do like weekly, not weekly, but more like probably year reviews, whatever it is, of the employees, of which the person that I know was an employee at this place. And they were like, all of the reviews, like several of the people got together and they were like, what did your review look like? What did yours say? And they all said the same thing. It was like, the person just used AI. And that's the other thing too, is that like a lot of the people, in my experience, it appears, objectively, are bad at using AI. Because like AI can give you a lot of good information and it can be very useful. It can actually be quite helpful to like supplement existing knowledge or existing work in a lot of cases. But if you're really bad at it, it will betray you, which is to say, if you just feed it like, here's a list of 20 names. These are the people who are my, subordinates or whatever. Write a review for them. And it's like the AI doesn't know anything about them. It's just going to write some generic thing like, person A has done an adequate job. They have been to work and done what has been asked. Like, what's it going to say, right? Like,
you have to feed it.
You have to feed it information. Like, here's some information. And it's like, the irony, of course, is that it's like, if you just feed the AI, you take the time to feed the AI, in this case, like detailed information about all 20 or 50 or whatever people. Well, you took the time to feed it to the AI, just write the reviews yourself. Like, why are you even using, like, you know what I mean? Like, the person that's going to use AI to just give them some auto-generated response is probably too lazy or frankly dumb to like to do their work, to do their actual job. So I'm being very vague here on purpose. The point is, AI can help supplement, like, give me a better way to, here's what I'm trying to say about what I think of this person. Please give me a way to word this that sounds more professional. Like, that is a way you might be as a supervisor. Let's say you're as a supervisor, you're like not a great writer, but you're a good boss maybe. And you're like, hey, AI, this worker's kind of bad, but I want to be like polite and diplomatic about it. Word me, write me a short response that sounds professional as a way to tell a employee that they need to work harder. Like that would be a good use of AI. You're just it's helping you find better wording, and then you can either use that or you can sort of modify what AI gives you. Like, these are things, but most of the time people are just like, tell AI to do things for them, and they don't even give it half the information, and it's just cheating. I mean, that's what it is. So there you go. There's my soapbox about it.
Thank you for coming to my TED Talk.
Thank you for coming to my TED Talk. Yes, exactly. We need a meme for that. Like, after one of us goes on a rant, which is usually me, I'll just change the thing in the middle to be "Thank you for coming to my TED Talk."
Yeah,
that would be funny.
All right, Jesse has a question. Jesse is asking, for my liquid electrolyte system, Na and Li symmetric cell for both, I found that it's volatile. I get high resistance, 12K, assuming ohms. Would that volatile state affect mass transfer? I guess I mean, some of the questions I have is like volatile state. Well, usually when we talk about volatility in chemistry, we're talking about like something's vapor pressure. Does it boil very easily? But I don't think that's what I don't know if that's what he's referring to here.
What do you mean by four? So the for both, is this shorthand for like FOR?
Yeah.
Or do you literally mean you have four
of each cell
electrodes or four cells? I don't know what that means precisely. So you have sodium and lithium symmetrical cells for both. I'm thinking what you mean is like it's like
FOR.
Yeah, like
for
like
both
just
of them.
shorthand. But because you have like if you have two sodium and 2 lithium electrodes, that's 4 electrodes. So that's why the number 4 is throwing me off. 4 equals 4. Okay.
4
Just checking. I'm making sure I don't
better equal 4.
Yeah, honestly, my brain was picturing some like complicated cell with like multiple sodium and lithium electrodes all over the place, and I'm like, I don't know. It seems volatile to me. Okay, so it's just a shorthand. No problem.
Okay.
Yeah. So for both of these, you're finding that it's volatile. Yeah, I guess. What do you mean by volatile?
Yeah.
Like, is it
like
is the potential all over the place, or is it
or is it
dangerously
actually
volatile?
like bubble, or is it actually like has a very high vapor pressure?
Yeah,
because it's liquid, which usually we say volatile liquids are ones that tend to have very low vapor. I think what would it be? Low vapor pressure, high vapor pressure, high vapor pressure, right? So that like okay, there's a lot of vapor coming up. It's volatile. And if that's the case,
evaporates, so it goes into
it
gas.
evaporates.
So yes, you are
okay,
correct.
all right. So volatile, it evaporates. Okay, so it's
comparing
volatile.
the lithium and the sodium system, it evaporates, so you get in the gas state. Would that volatile state affect mass transfer? I mean, for sure. The properties of the electrolyte will absolutely impact mass transport. You know,
if this cell is sealed, right? I'm assuming these are all batteries, right? And they're
not necessarily. It could be like in a glove box.
Okay.
Why is it so volatile? Like, what's your solvent? You know, most electrolytes are like carbonates, and most of them have very high boiling points. You know, I guess I'd wonder, why is it so volatile? Why is it evaporating so readily? Some electrolyte solvents for like lithium ion batteries, for instance, are so not volatile that they're solid at room temperature. So like ethylene carbonate, for instance, is like you get a beaker of it, or like a the amber glass like thing of it or whatever. It's like crystals. It's sealed and testing impedance. Okay. That doesn't sound like a good sign. I don't know why your electrolyte would be evaporating so readily.
And it's he's saying high resistance.
Yeah, that's not surprising because you don't have any electrolyte. It's all in the gas phase, or it's at least evaporating. So a lot of, or some parts of your system are probably having trouble having a connection. Like
so there may not even be liquid.
Yeah, if you don't have a liquid
in the cell.
If you don't have any liquid, or you have less of it because somehow your solvent is so volatile it's evaporating, you're going to get pressure buildup. That's a problem. You're also going to, you don't have a electrode electrolyte interface. My electrolyte is using low molecular weight polyethylene oxide. Low molecular weight okay.
Well, that's probably a volatile thing.
Yeah. So I mean, you're just. I mean, I guess that it's certainly if you're sort of polymer electrodes. Okay. Yeah. I mean, honestly, if you can't get your electrolyte to be in the liquid phase for any appreciable amount of time, you either have to decrease the temperature, which presents its other dangers. Doing cold charge discharge could be not a great idea in some cases. But
actually, that's a whole field of having batteries in low temperatures.
Yeah, it's you get dendrites and stuff at low temperature. It's really tough. But if you decrease the temperature, like if you can go slightly colder, I mean, you'd have to get some chiller or some, it's hard to just decrease the temperature. You have to have some temperature control device of some kind, right? But if you decrease the temperature, presumably you would make the electrolyte less volatile because vapor pressure goes down with temperature, basically, usually. So, that's one possibility, but it's like, absolutely, your mass transport's going to be a problem. The resistance is going to be high. If you were to make a battery, for instance, symmetrical or otherwise, and just intentionally add no electrolyte, like add no liquid on purpose, but make your battery otherwise the same. So you have an anode and a cathode, whether they're symmetrical, the same, or they're different, it doesn't matter. And you have a separator in between them. You could probably get a potential out of it. Like you'd probably measure something because it's like pressed together. Like if you made a coin cell and you like press it together, like there will be some parts where the anode, is touching the separator and is touching the cathode, and there's like a possibility for like ionic transfer, like they're touching enough that you'd get a voltage or whatever. But if you try to do electrochemistry on it, it's going to be miserable. Like it's going to be bad. You're going to have really high resistance. It'd be everything you're describing, because it's like the same situation, right? It's like no electrolyte on purpose. So the impedance is going to be preposterously high because there's no like, there's no electrolyte, there's no like abundance of ions to complete the circuit very easily. You're like waiting for the like school children of lithium ions to like make their way across the membrane instead of having saturated membrane, ions present in solution, which is what electrochemistry is for. So what you're describing is like a situation where the electrolyte is evaporating, and like to say that it's causing problems with mass transfer is to say that there is no mass transfer. There's no electrolyte. It's like you don't even have any, barely. You don't have really any ions, hardly, there at all. Or if you do, there's no liquid for them to be able to move. It doesn't surprise me your resistance is really high. So you're going to have to find a way, pressurize it or decrease the temperature or use a different electrolyte. I mean, I guess if that's what you're studying, you're kind of stuck trying to use it. But if it's just evaporating and it's barely in the liquid phase, I honestly don't know how you can even bother get it, like how it's even possible to get electrochemistry with it basically at all. You have to have liquid. You have to, or if it's a polymer, I know it's a polymer electrolyte or whatever, but like you have to have connection between the two sides. So if you have really high resistance, you just don't have really hardly any connection between the two sides. So something like that.
Yeah, I was thinking about if you could get your liquid, even if it's volatile, into the cell, seal it with liquid such that it didn't have super high resistance, would that liquid affect mass transfer? And I would say the answer is still yes, because I'm sure the ability for lithium and sodium ions to diffuse through the battery is a function of the solvent that you're using, the electrolyte that you're using. So it may diffuse more quickly, but this is again assuming you could actually get the cell and pack it with this volatile electrolyte. But from the sounds of it, it's like it's evaporating before you're able to fully seal it.
Yeah.
So, but I don't know. Good luck, Jesse.
Yeah, good luck. That's the best I can say, I guess.
It's a little that's hard. I think it's hard. Hopefully what we said is helpful though. Maybe if you, I don't know, had like a bath of dry ice or something, and you had your cell on it, and you could pipette in the glove box this your polyethylene oxide, and actually have it stick there long enough that you could press it in, seal it quickly. Crimp it so that you do have it.
Because maybe it's evaporating before you even like put your cell together. So not only is it evaporating in the battery, it's evaporating before you make the battery. So like if you can cool it down while you're making it, you'd ensure you actually have the electrolyte solvent there in the first place, right? So
I'm also thinking I feel like volatile electrolytes and batteries are definitely a bad thing. Like we don't want to have those because like there can be pressure builds up, all that kind of stuff. So something to think about. But
Yeah.
For research purposes, maybe it's useful. All right.
Not sure how to answer this exactly.
Yeah.
Preet Viraj has said, please explain metal insoluble salt anion.
Metal insoluble salt anion. Not so sure. Most metals become cations. They tend to have positive charge instead of negative charge built on them. It's a very highly unstable configuration for most metals. But the solubility of a metal. So normally, you can have insoluble salts, and the salt is just a metal and a non-metal together. That's all a salt is. So if the metal is insoluble, just what is it like? Silver chloride. Like silver chloride is not very soluble. It crashes out of solution, and turns to if you have silver ions and they have chloride ions and you put them together, like if you mix silver nitrate and potassium chloride, you get this white precipitate. It's silver chloride, and that's because the metal is insoluble in the solution. But you're talking about a metal insoluble salt anion, and I don't know. It's the anion part of that I'm a bit confused about.
Is he asking about is it like a complex? You can have like Fe with a bunch of stuff around it, and it has a negative charge, and that's like an anion. I know there are some things like that, but I don't have a lot of experience with them, or I think there's things like that.
Yeah, I mean,
like complexes that are negatively charged.
Are those? Yeah, so I can understand having a net negative charge on a complex while having like your counter ion somewhere else. Like maybe the negative charge is localized on like the ligand or something.
Yeah, something like that.
But then, and those can be insoluble depending on the solvent that you're working on. Absolutely. Because solubility is just based on the solvent that you're working in. So even if it's not soluble in water, maybe it's soluble in toluene or something like that. You can do that. So,
I mean, the solubility. I was just sort of fill that in just as a note of chemistry here is that if you have some salt that's AB, right? So this is like A is metal, like you were saying, right? And B is a non-metal. So this is like AgCl or whatever it is. So this is a non-metal, non-metal. The dissociation reaction is like A, B, goes reversibly to A.
See, he says acid at anode and AgCl at cathode type.
So what is it?
It's just the next
acid at anode and AgCl at the cathode type. I don't know what this means per se. I'll just finish this one thought. I don't know if exactly, but like the K, we sort of write an equilibrium quotient, so to speak, and it's basically the concentration or activity of A times it's the products over the reactants over AB, basically. And so when we're talking about something dissolving, we call it a KSP, solubility product. And so typically a KSP, might be something like, for something that's not soluble, 10 to the -9. I don't know, something like that.
Yeah.
So like that means that we have like nanomolar concentration of A or B, right? A or B dissolved, compared to the concentration of my AB or the whatever, that which we just use a unity, right? So, but my point is here that we're typically in the situation where we're showing that there isn't a lot of this forming. Maybe that's not exactly what you're asking. I just thought I'd finish the idea about KSP.
Yeah.
But I guess I don't know I'm not sure precisely what you're asking, to be honest. We might have to sort of pass on this at the moment. Acid at the anode and AgCl at the cathode
Cathode
as
type.
a type. Acid at the
Yeah.
AgCl cathode and acid anode. I don't know what you're referring to precisely here.
Yeah.
I think I'm kind of confused.
Yeah.
So I'm not sure, to be honest, what you're asking or what the system is or what the question is even, to be honest. I'm a little confused. So apologies. If there's a way for you to sort of type or clarify kind of what you mean, please try to do that, I suppose.
Yeah.
Otherwise, I think we might just move on. I'm not apologies, but I don't really exactly know what you're asking.
Thanks.
Yeah.
Okay.
Sorry if it's not super
Yeah.
helpful, I guess. But okay, so we have another question from Abderrahim. Says, can you talk about pulsed electrodeposition? Well, we did talk about DPV earlier, so I don't know if you want to fill in some of that.
I will at least mention that there are people who are playing around with, most of the time when we talk about electrodeposition, people usually just apply a potential or run something in constant current mode galvanostatically to deposit stuff on an electrode. Of course, when you deposit things on an electrode, the shape of the surface is a function of many things. A lot of people like to stir the solution. There needs to be a certain temperature. That'll change that will basically change a little bit of how it deposits. You may get something that's smoother, or maybe you can form a special crystal face, or you can get the thickness a lot faster, stuff like that. But to my understanding is that there isn't really a lot that's very well known about pulsed electrodeposition. I think a lot of people play with the parameters of because normally in techniques like DPV, you're maybe holding the potential for milliseconds, maybe hundreds of microseconds when you're doing these pulse techniques. But when you talk about deposition, you actually still need a little bit more time. When you apply a potential in some kind of pulsed manner and then retreat to another potential to kind of regenerate the diffusion layer, that's like a technique people play around with the frequency. They play around with how long you hold the potential. They play around with the potential itself that you pulse between. So, and what I hear is everybody's really just trying things that are new. I don't know, mostly because I don't read the literature. We don't have access to the literature. So we actually don't know. People have tried a kind of square wave, I want to just pulse for 2 seconds at 1 volt and then 0 volts on and off for 2 seconds each at 5,000 times and let the thing run for hours. And okay, and then maybe from that they get some useful, they got a certain kind of surface that's unique or very different from what they've done before. So it's tricky. Mostly traditional electroanalytical chemistry techniques are not used in pulse deposition. Things like square wave and differential pulse are just used as analytical techniques, figuring out how much or if I have a certain amount of a particular species. But it's not for putting something, coating something on a surface or on an electrode. And people are playing with well, how long do you do it for? At what potential do you do it for? Do you cycle back and what's the potential that you cycle back to? So usually people make their own pulses or their own experiments where they're going back and forth and back and forth. But yeah, the time, how long it has to pulse for, and then how long, how often do you do it? Those are all things that I think people really just experiment with. They really don't know for sure the science behind it. And when I pulse like this, I get a really smooth surface. But when I pulse like this, I get a rough surface, but I'm able to get more molecules on the surface per per time or something. So
I think it's also like you pulse. Sometimes people pulse like instead of up down, like the pulse, potential if it's negative or whatever. If it's if you're depositing something, it's probably a negative potential. But and then it's like, what's the other potential? I think in some cases it's like it's off, like it's open circuit, like it's like a on off thing. So it's like between no potential applied and then a potential applied.
Yeah.
So that's one possible way, I guess. The only two things I know about something like this is that like we have our company has a customer who like I visited them years ago, and I don't 100% know. Like I was trying to help them build some experiments with, they have, some of our equipment or potentiostats and things like that. And they were doing some pulse technique. And I don't know if it's like a deposition exactly, but they were doing a thing where they were pulsing like really high swings of potential. And it's just as you said, like they were trying something
stuff.
And I don't know if they were like exactly sure, like, it's like plus 8 volts, minus 6 volts. And they were just doing some crazy, it was crazy, like swing of potential. And it was like, wow, like, I don't know what you're going to get from this, but they had some reason for doing it. And in any case, it was a similar thing. It was like, they were doing this pulsing like a, like a strobe light with their potentiostat. Maybe they're trying to program a disco nightclub.
That could be it.
That could be it.
Yeah.
But anyway, that was one example. And then the other was that I there was this one like group that I think I saw years ago, and I don't know, I saw like a presentation or a poster at like a trade show. So it's been some time, and I'd have to look into it a little more. But they were doing some kind of pulse technique for battery experiments, and supposedly it was like helped longevity of charge discharge. Like instead of just doing a C, like 5C or C over 3 or whatever the rate, like applying a current and whatever, they were pulsing either the current or the potential, like on off, kind of like pit or get, but like faster. And doing that was supposed to, prevent possible like failures or safety problems because of the having like rest time, but even that would make it take longer in theory, like because you have some time where you're not charging or discharging. So I'm just throwing that out there as it's just another, like, to your point, like most people who are doing this kind of thing are just sort of trying stuff. Really, it's like, hey, what if I just do this? I don't know, let's see what happens. It's like, and otherwise it's a diagnostic, like DPV or whatever else. So for sure.
Yeah, that's true.
Well, we have a couple of minutes, so we're just about at time here, but I could share this funny new video series.
Oh yeah,
that I made. I just recently made a very ridiculous set of videos where they're called research pitch meetings, and since we have no questions in like just a few minutes remaining, I think what I'll do is shamelessly play for you this first episode of my research pitch meeting. I think it's sharing the audio. I don't actually know if it's sharing the audio. That would be a big thing to do.
Well, when you share, it should be able to select.
Let me redo it because I don't remember if I picked that or not. Right?
Yeah, it says also like share audio tab or something.
Yeah, I think I am sharing the audio.
Okay.
So okay, perfect. So I'll redo it again. So yeah, I'm just gonna play this little short 1-minute video for you. And I hope you think it's funny. I think it's funny, but I might be the only one in the world, and that's possible. But anyway, I made these, and they're on our YouTube channel, and I hope everybody watches them. So you have a research project for me? Yes, sir, I do. So you know how batteries power basically everything in the world these days, like phones and laptops and cars? I do, yes. Actually, come to think of it, every time I'm giving a lecture using my battery-powered laser pointer, it dies halfway through class. Maybe I'm pointing at my slides too much. Oh yeah, you might want to rely on that thing a little bit less in class, sir. But either way, I think I might have a solution for you. Oh really? Well, that would greatly help with my propensity for incessant laser pointing. Definitely, sir. So what I was thinking was, what if I told you that your laser pointer battery could last twice as long so it never dies during your lectures in class, and you wouldn't have to replace it for at least 4 or 5 years? I'd say you're a stark raving lunatic who doesn't understand how science works and that you should leave this research group immediately. No, sir, what I mean is I think that we can develop a new cathode material that would have double the gravimetric capacity and retain close to 100% Coulombic efficiency over thousands of cycles. Oh, that sounds a lot more reasonable, and it makes me think you might be capable of electrochemistry research after all. Thank you, sir. You're welcome. But since you're new to my research group, I'm honestly just a little bit skeptical. You know, I'm guessing there's at least like 27 things that you probably need to know now that you're starting your PhD. Hi, thanks for watching this video. I hope you enjoyed it. Please give it a like and subscribe to the Pine Research YouTube channel for more great educational electrochemistry content. Also, a quick shout out to Ryan George of the Pitch Meeting channel for the inspiration behind this video. Thanks a lot. See y'all in the next one. There you go. Very exciting. Just some funny little content there. It's obviously not education. You're not going to learn anything, but I hope you'll have a laugh. They're all pretty short. It's like a minute long. So I've made a few of these episodes, and if everybody watches them, I would appreciate it, and hopefully it gives you a bit of a laugh. So there you go.
We did get a question right at the end here from Paris. He's asking, hello, I want to determine whether a solid oxide electrolyte material has ionic conductivity properties or not. How can we determine these properties using EIS? I don't understand the main logic.
Maybe a 4-point probe, I guess.
Yeah, how do you determine whether it's ionically conductive or electronically conductive?
Well, ionic conductivity. So I think the electronic conductivity is the one that we do have a problem measuring, but ionic conductivity in theory is the one that we are measuring when we do a sort of a quick polarization kind of a thing. So here's the logic. Now there's some other open questions because you're saying a solid oxide electrolyte. So typically like solid oxide fuel cells or things like that are usually like YSZ. I don't know if that's what you're referring to. It's something like that, which is typically something that has no conductivity, like YSZ, for instance, yttria. I don't know, is it yttria or yttria? Like YTTR, you know, that element that nobody knows how to pronounce.
Yttrium or something.
Yttrium.
I think so.
Anyway, yttria stabilized zirconia is an insulator at room temperature. It only ionically conducts at like 800 degrees Celsius or 600 or something like that. So if you're referring to that, what I'm about to show you might be physically very difficult to accomplish. But generally speaking, the logic behind measuring ionic conductivity is something like this. If you have a membrane or some kind of a material you're trying to measure its ionic conductivity, if you have a flat portion of it or something like that, what you do is you take your electrode leads and you're going to have lead here. This is going to be your working sense line, and you're going to have your reference line from like a potentiostat reference line. And you're going to put those sort of on the material in some place. Okay. And then you're going to have two other lines, which is you basically have them anywhere else essentially, which is the working drive. Okay. And the counter line. Okay. What you're doing here is either impedance or a very short polarization. And you have certain knowledge, which is that this distance here is some distance. And you want to generally make this pretty small, basically, between the two sense lines. And what you're doing is you're either doing a quick like polarization, let's say around like the open circuit. You're just going to like sweep a few like 10, 20 millivolts back and forth or whatever. And you're going to get the slope of this line because V is IR. So basically you can get a measure of the resistance. That's what you're after. Okay. Or you just do impedance, and impedance gives you a measure of the resistance as well. And generally speaking, the conductivity, which we sort of say ionic conductivity, sometimes I think we use the sigma, is something like D over R. And then this always trips me up actually, because there's like a surface area term. So I don't know if that's like like all of this surface area, or it's just like some surface area here? I'll be honest, this trips me up a little bit. So apologies if this isn't like a perfect answer, but you might have to look into this a little more. But this is roughly how like a 4-point probe to get ionic conductivity works, is like, what's this surface area? I'm not 100% sure, to be honest. But basically what you get from this expression is, you know, like meters divided by ohms, resistance is ohms, times meters squared, right? So meters cancels and you get like Siemens per centimeter. You know, so let's say centimeters instead of meters, because usually it's smaller. So this is usually the unit that we use for like conductance or conductivity, ionic conductivity. So it's something like this, but from an electrochemistry standpoint, the main thing is that we're basically trying to measure the resistance. And the reason we dissociate the sense lines like this is because we don't really care about the current, the voltages across the drive lines. We're trying to like minimize the distance between the sense lines to get a very careful potential measurement. So we bring the sense lines as close together as we can. It's kind of a measurement here. So was there any follow up or something?
No, there was no follow up. I think one thing I would say, because part of his question is that I think he's trying to determine whether it's ionically conductive or not.
Yeah, I sort of showed how to measure it if you can,
but I think to your point, it's like if you had a pure electrical conductor and you did that same kind of thing, you'd measure a short circuit, because it's like hooking up a voltmeter to a platinum wire. It's like purely conductive, short circuit. But if you hooked it up to like a chunk of wood, something that was an insulator, you'd measure like OL on like a voltmeter or something like that. You'd get no signal. So, but if it's an ionic conductor and you have an electrolyte with some kind of ion in it, there's a couple things. One, maybe you have some control over adding more ions to that electrolyte such that it can conduct more. So you can test, if you get something that's not short circuit and not open circuit, then it probably conducts ions.
Yeah.
And if you add the ion that you think your electrolyte conducts, you should see some changes in the resistance. And EIS can be a way of looking at that resistance change, but also the 4-point probe technique that Neil just mentioned.
Yeah.
So I'd say that's the other thing.
Yeah, that's good.
Yeah.
And yeah, I get the only other thing about that is if it's a solid oxide fuel cell kind of a thing, it might require high temperature. So everything I'm showing might be physically difficult to accomplish, but in theory, it could still work even at high temperature if you can get the probes to survive the temperature and all the things. So, okay, I guess we'll call it there.
Yeah.
So thank you, everybody. We appreciate the questions as always. Appreciate your support. And I hope everybody has a great week. We'll see everybody next week.
All right. And don't forget, if you haven't, you should register on the Pine Research website under webinars. You can register for the Mott Schottky webinar Neil will be giving on Wednesday. And I believe even if you miss it, you'll still be able to watch it for a little bit of time before
it'll be on YouTube for a couple weeks. We'll leave it there until then we'll eventually join the webinars that are for tier 2 members only. But for a bit, if you miss it live, you can watch the replay of it and watch it as though it's live, basically. But joining live is good because you can ask questions and I'll answer them live. That's sort of the idea, right?
That's the idea.
So anyway, to everyone who joins me in the webinar next Wednesday, thank you in advance. And to all of our live stream viewers, we appreciate you. Hope everybody has a great weekend.
All right.
We'll see you next week.
Bye.